Okay, so it's being recorded now. So you want to go with the first question?
Do you want to go in order? I finished the homework, most of it, at least, but I'm not sure that is correct everything. Then I would like to, like for example, in the exercise 3,
Okay.
which was more complicated. Maybe can we start in exercise 2?
Exercise 2, let's go back. So let me open just exercise 2. Should I use Blackboard? No, maybe better. Okay, wait for a second. So I'll find it and then I'll share it. Okay. Stellar Revolution. Okay, fine. Number 3.
You want to start in 3 or you want to start in 2? I'm not sure the rest. Everybody have that?
I don't know, actually. I only see you, and I don't know who is the second person there. I think Ryan is online, but I cannot hear him. Ryan, can you hear me?
Yeah, I can hear you.
Okay, fine. Fine. So what do you prefer, number 2 or number 3 file for the homework? Let's start with number 2, okay? So let's share number 2. Let me see. Okay, so number 2. Here is number 2. Okay, so you have an HR diagram, and then you have points A through E. And then the question is, rank from earliest to latest the stages in the life of a low mass star without a companion. Okay, so well, what do you say?
The first one will be D.
Okay.
And then I think because the B and C are in the same sequence, B.
Okay.
The second one, B. The third one will be C.
Okay.
And then you will go to E.
Okay.
And the last one, A.
Okay, what do you say, Ryan? Agree or don't agree?
Yeah, sorry, I was doing something right now. I'll have to get back to you in just a second.
Okay.
Sorry.
Well, you have to participate. You're the second person. Okay. Okay, so I'll wait for him and
no problem.
So, Rosa, what do you say? These points C, B, and D, where are they? What is that? Can you identify, let's say, these regions on the HR diagram?
Well, you're saying that they are in the main sequence?
C, B, and D?
Yeah, you put the note there. Note that the only stars B, C, and D are in the main sequence. That's the information. And I'm assuming that the star C is a blue giant.
Okay.
And B is a little bigger than our sun because it looks too high for me.
Okay, I agree with you.
And D seems to be smaller than our sun. Then I'm thinking our sun is between B and D, a little higher than D, not too much.
Okay, fine. So yes, I agree. Our sun is between B and D, closer to the D than to the B. And so, so
E is like a giant, some type of giant. A big giant. And star A is like a white dwarf.
Yes, it is. So then why are you saying that? And so you're saying now that the star D is basically lower mass than our sun. So for sure, that's a low mass star. And you said that C is the blue giant and B like a little bit less, let's say, hot than the blue giant. So are C and B then low mass stars or high mass stars?
High mass. I think they are bigger than our sun. Yeah.
Okay. And so then why do you say that? So I agree with you. They're high mass stars based on their position on the main sequence. So why then, how can low mass star evolve from basically being low mass to becoming high mass? Is that possible?
No, I have like a giant after being high mass. I had D first.
Yes.
Then B, then C, then E, and then A.
And so I don't agree with that. So is Ryan here or it's not?
Yeah, I'm here.
Okay, so what do you say now?
I'm going by what?
So she's correct that D is the low mass star when you're looking at the main sequence.
Yeah,
D
which is a bit long. Yeah.
And C and B are not low mass stars; they're high mass stars.
Yeah.
And the question is, rank from earliest to latest the stages in the life of a low mass star.
Oh, I see what is my mistake.
Okay, good.
I will let him correct me if he can see it, and I tell you just in case.
Okay, so I don't know, Ryan. You want to? What do you think?
I'm going. Whatever. Obviously, low mass star. So it's going like okay. I guess I'm trying to understand the low mass. Like, is it stages it's going through? But I don't.
Mm-hmm. So did you
I
see?
wouldn't know. I would honestly. I'm not sure. If there's like, is there enough information for like? I don't really know.
Yes, there is enough. Okay, so Raul, so what did you figure out now? What is the correct sequence here?
Okay, D is the first one,
Okay.
the earliest. Then will be AE.
A you said is a white dwarf. So the main and E you said is the red giant. So the main sequence star, low mass star, low main sequence star. So what does it do? Does it immediately after main sequence becomes white dwarf?
No, but that's what, okay. In the main sequence has to be a and then we die like a giant.
Yes. And then at the end, basically what is left after white dwarf. So that's it. You said it. You just have to now, and you identify the letters. So first goes the D, right? So the main sequence, a low mass star on the main sequence is somewhere here in this location. That's where the low mass stars are. So these two are high mass stars. So you don't even consider them. They're disqualified.
Oh, we don't have to put them on? Oh, okay.
Yeah. So it's a low mass star. After it finishes.
Put all the letters. That's what I put BC because I was choosing in the main sequence.
No.
The first one and then BC because I had to put them because they were main sequence.
No, but it says low mass star. So the first thing that you have to realize over here is that C and B, and you did that. C and B are high mass stars, and D is low mass star. So then you just choose D. That's it, and you're ignoring then B and C because they don't qualify to be low mass stars.
Okay, then it's important. The instructions is low mass star. I did not read the low mass star.
Okay.
Just take out BC.
Okay, good.
Okay.
So after main sequence, the low mass stars will become giants, and then they will finish their life as the white dwarfs, and that's what you are ranking here. Okay, so that's this one. Next one.
I'm not sure. Is your name Ryan?
Yes, his name is Ryan, I think.
Do you want to check number one? Because I have it ready, and if you want to check, maybe that will help you. I'm ready to go to 3, but if you want to check 1, it's up to you.
I'm getting a little bit of what you're saying. I can't.
Okay, so she's asking if you're interested in going through the file number 1.
Yeah. Do it, you guys. Yeah, I'm observing. Yeah, you guys are good.
Okay,
I'm
so
perfectly fine with going through that.
Okay, here is number 1. So what do you say over here?
I let you do it. I have it ready, but if you want to try.
Ryan, you try.
Okay, I mean, I would go CADBE.
Okay, good, because.
Well, I guess if you're going, yeah. If you're going from least to most, it's going to be EBD.
Sure.
Yeah.
Okay, and then how about the B, temperatures?
From hottest, you're going to go CADBE.
Okay, and why is that?
Well, I know that like the bigger they get, like that was the was it? No, wait, they got cooler. I think. It was like the bigger they got, the hotter.
Yeah, that's it. So the bigger they are, the more mass they have, then there will be more gravity on the core. So the temperature will be higher, the fusion rate will be faster. So the star will be overall hotter and more luminous. Okay, so that's good. So what you see over here, C is the biggest star, so it's going to be the hottest one as well.
Mm-hmm.
Okay, and then luminosities?
Like the greatest. I'd say CADBE.
Exactly. Okay. And then how about lifetimes?
Total.
Hello?
Sorry, that was a car that just drove by.
Okay.
Let me close the door real quick. Sorry. Rank from longest to shortest tone. I would say it's gonna be E, B, D, A, C.
So who lives the longest? The lowest mass stars,
E.
right?
Yeah. Yeah.
Very good. So on the main sequence, because this is all related to the main sequence, on the main sequence, you know that those smallest stars, they can live even like trillions of years, so more than the current age of the universe. Exactly. Okay, that's very good. So then number 3, I guess.
Oh, then, all right.
Okay, so let's.
What about you?
I have a quick question.
Yes.
I mean, not regarding the homework, but did you see the video of the asteroid?
Yes, I did. Yeah, I did actually.
I haven't watched it yet, but I was wanting to check that out.
Oh, you mean like if I seen it like on the internet?
Yeah, because I know it went by, what was it, 2 days ago?
Yeah, it was actually, no, it was, I think, yesterday, last night, it was closest to the Earth.
Okay.
Yeah, and it was really cool. I seen it, and actually we had the Astronomy 109 lab. I think they were on the roof trying to take a picture of that asteroid as well. So,
Wow.
yeah. So, yeah, very cool.
They were really good with the camera. Look how they were taking with the telephone.
Wait, Rosha, I did not hear anything. Somebody has some background noise. Okay, so say again, Rosha, what did you say?
Many of your students were taking pictures. Wow, incredible pictures.
What did you say?
They were taking pictures with the cellular, beautiful pictures with the telephones. Wow.
Oh, really? How do you know?
Because the last star party, I saw how they were doing it, and that was very nice.
Oh, I know. No, but they had cameras now on the telescopes mounted, and I think they exactly wanted to do that, to take a picture of the asteroids. That was by the schedule, and then it turned out that this asteroid came actually really close, so they were able to take those pictures. Yeah, I think they were very happy with the development.
Wow, that's nice.
Yeah. Okay, so here is the exercise number 3. This one is hard, okay? So this summarizes kind of
I started with H.
And this is even maybe like a little bit ahead, because this would probably, it would be easier for you to answer this after next week's. But so let's see how you're gonna do this time around. So what do you need? Rank from earliest to latest the stages for a low mass star without companion.
I started with an H, molecular cloud, gas and dust.
Okay.
And then I went to M, gravity collapse of gas, dust, and dust cloud.
Okay, fine.
And then I went to B, G spectral class main star, you know, like our sun.
Sure.
And then I went to, where is this? Giant, and F. And then I went to A.
Okay.
And then that's I.
I, very good. That's excellent. That's it. Perfect. So basically you start with a cloud of gas and dust, and then the gravity will make it to shrink and collapse. And then you form like G spectral type star, which would be the low mass star. And then after that star, let's say like our sun spends 10 billion years fusing hydrogen into helium. It uses up all of the hydrogen, and then it becomes giant. During the giant phase, you don't have like nothing in the core is fusing, but the shells are fusing, and that's why they basically inflate the star. That's why it starts expanding. And then after for the sun actually, or for the low mass stars, will the core fuse once more?
The core, no. The core, it will not fuse. The shell. The shell has the fusion now, and then start growing.
Okay, but eventually, okay, will the core, so why the core is not fusing? Because simply the core is full of helium. For helium to fuse, you need much higher temperatures than what the temperatures were when hydrogen was fusing. And
the star begins to contract, and the atoms in the core move faster.
They do.
And eventually,
And then they kind of create like another helium shell, but then it can't fuse anymore besides that.
So basically now that hydrogen that it's fusing in shells, it's going to create helium. So on top of that core that is shrinking, you will be creating now helium. But my question is, what about that core that it's full of helium? Is that ever going to fuse again? Will it fuse helium into carbon?
Yes.
Yes, very good. So eventually the whole core then will become hot enough, so it's going to fuse again, and it's going to fuse helium into carbon.
And also it says that sometimes nitrogen and oxygen.
Yeah, but you can ignore that. Yeah, well, so we're just going to do like a very simple picture of it.
Okay.
Okay, you are right. Depending on the mass, they're not all going to take 4 hydrogen and create helium. There are different ways, but that's not important, kind of. I'm going to ignore that. So just the big picture, and because there is anyways too many details and too much information. Okay, and so...
The next one in the B, rank from earliest
No,
to
wait. Let's review now. Yeah, wait for a second. So let's just review this. So the core eventually will fuse the helium into carbon, and then what will happen? What happens when you make now the core full of carbon? Will the low mass star fuse anything after that?
No.
No, very good. But once again, when the fusion stops, the gravity starts shrinking the core, and now you have those 2 shells are going to fuse, the hydrogen and the helium shells, and that's going to expand now star even more. And that's the planetary nebula, right? That's that of a low mass star. And what is left behind is the white dwarf.
Yes.
And that's it, basically. You're done with the low mass star. Now,
All right, chapter done.
No, you still need high mass stars, right?
I have something interesting that it says that luminosity increase, temperature decrease.
Yes.
And just because the luminosity is because the big mass, because it's growing so much, expanding so much.
Not because of the big mass.
Big mass.
No. The mass does not change, right? Whatever mass star had on the main sequence, I mean...
The size of the red giant expands, and that keeps the luminosity?
Yes, it does. So luminosity is not because of the temperature, because temperature is low, but it's because of the huge size.
Huge size. Thank you.
You're welcome.
All right.
Okay, so now I think B, you still don't know how to do B, but let's see, what did you say?
I have it.
Okay, you have it.
I'm sure it's right.
Okay.
HM.
Okay, so it's the same, the beginning is the same.
Yeah, HMBF until there are 8. HMBFA.
Mm-hmm.
Okay, it's the same. I.
Mm-hmm.
And then you go to L, Nova.
Okay.
And then K.
Maybe, right? So if the white dwarf has a companion, it can go nova. And then if it...
In this one says that has a companion.
Yes, I know. So B is if it has a companion. But, okay, I'm going to review the homework. I'm going to... what's the smart thing? Maybe I should move this homework for the next week, okay? So because in the next chapter, you will learn about these things. So about nova and supernova type 1. So that's what I will do, okay? We can still...
In the next homework, there is something that you put the star evolution.
Yes, the next home...
That says, you make us do circles. And after the white dwarf has a binary companion star, has 2 choices. Either it becomes a nova or a type LA supernova. Type 1 supernova?
Yes, that's true. That's true. You're correct. So you'll do very good on the reading questions that are coming up.
Oh, I'm not sure. Can we do the other ones or?
Yes. So only B actually you don't know. So let's leave the B, but C you should know. What happens now to the C?
Okay. H, M, B,
Mm-hmm.
F.
Mm-hmm.
F is the giant, and then it's going to be D or C, DC. D is going to be a supernova type 2, or C, a neutron star?
Well, it's going to be the supernova type 2 for sure. So what did you say? You said H, and then M, and then G, right? The O spectral class main sequence star. That's good. So that's the high mass star. And then it's going to go through the giant phases, supergiant phases, whatever. And then it's going to go supernova. And then
1 second. It's 8 M B F then D super type supernova.
And then what did you say after supernova? What is left behind high mass stars?
Neutron star?
Or?
Can be either one, neutron star or supernova, supernova, neutron star.
Black hole.
Okay, good. So supernova happens for sure. So there is nothing there to doubt. Supernova happens for sure. And then what is left behind is going to be either neutron star or black hole, okay?
1 second, I didn't have that one. Black hole. Thank you.
Mm-hmm.
And you want to do the last one? Or you...
So that's basically, the last one is the same, because it just now asks you for the most massive high mass stars.
Okay.
So the most massive are going to leave black hole, let's say, and C should be neutron star.
So D would be black hole.
Yes, and C
Why would it be black hole instead of neutron star?
Because that's what you're learning this week. That if the star has between 8 and 20 solar masses, at the end, actually, all of those stars, everything that has more than 8 solar masses is going to fuse beyond that carbon, and it's going to fuse all the way until there is iron in the core. Right? Do you remember that that part?
Yeah.
Okay, so now the question is what happens with this iron. The iron will not fuse, so regardless of how high the temperature is. So it's just like sitting there and the gravity is squeezing this iron. And so now what happens with the iron, the electrons are somehow pushed towards the nucleus, and so you have the reaction between electrons and protons. Let me just stop this, because I'll go to the blackboard where I posted those things today, because that tends to be hard, and so I kind of singled out that supernova type 2 explosion, what happens there. Okay, so okay, so okay, so let me now just share this. So this is what I want to share. Okay, so this is now on the blackboard, and I posted that this today. So this is now what happens inside of the core. You have completely, like, you have a core full of iron, doesn't want to fuse. So what you have now, the gravity pushes all of these electrons, and they react basically with protons. Protons are in the nucleus of the iron. And so when you have that, then what happens, you form these neutrons and also neutrinos. Neutrons are important because that means now this core is fully made out of neutrons, and we call that the neutron star, right? And so that's the neutron star. And neutrinos are important because they are going to drive the supernova type 2 explosion. They have so much energy. And in one of the Crash Course episodes, they tell you 100 times as much energy in 1 second, basically, goes with neutrinos than is produced throughout the sun, the life of the sun. And so they will drive the supernova explosion of the star, but this is what is left in the core, these neutrons. And so every single high mass star does that. But now, depending on the size of that core, and I think that comes in the next chapter now, if the size of the core is more than 3 solar masses, then the neutrons will get destroyed, basically, and so the black hole will be formed. But if the star, we say, is
what is left, if the star is more than 3 solar masses, then
no. Once again, all of the high mass stars are more than 8 solar masses. So all of this, basically, fusion and this supernova type 2 explosion happens for stars that have more than 8 solar masses on the main sequence. However, you do know that even like sun, when it dies, it will return half of its matter basically back to the interstellar medium, right? So the core that the sun leaves behind will be very small. So the same for these high mass stars. They were big on the main sequence, more than 8 solar masses, but now this core that they're leaving behind is going to be much smaller. And so it turns out if that core is less than 3 solar masses, it will produce neutron star. So the neutron star will be left after the high mass star. But if that core has more than 3 solar masses, then what will be produced is the black hole. Does that make sense? So once again, the next week we will go into all of these details. That's in the next chapter. But so I just wanted to tell you, so that's the reason. Okay, so if they are intermediate kind of a high mass stars between 3 and 20, we can work out the physics that they will leave behind the neutron star. But if the stars are really big, more than 20, 25 solar masses, they will leave behind the black hole. So even these neutrons will get destroyed.
Yep.
Okay, does that make sense?
Yes.
Okay, very good. So I put that, if you see over here, the number 5, that's where I actually summarize that. So you can read that. And then the next week, we'll go into more details in all of this.
Number 4 in the star evolution.
Okay, let me stop sharing this. And then number 4. Okay. Oh, yeah, I remember that one. That's with the clusters. Okay, fine.
I have something I really think small explanation will be good. I have DCAV.
Which one is youngest? You're saying D is youngest, and then C, and then A, and then
D.
B. Very good. Why do you say that? Can you explain?
Yeah, I started with the first ones, but you know, because where they are, the first one is like a.
Are you there?
Yes, I'm just thinking. Like the first one, I just saw it in the main sequence. I just was looking at the stars and saw like the first brand new main sequence, and then I think they start, you know, changing and they start moving out to the right.
Yes, very good, Rose. Excellent. So
it's not a very scientific explanation. I just saw the stars moving to the right, and I figured out that more to the right is the older star.
Okay, fine. So if we look at this D, if you look at the plot D, so what you see over here, we said the stars are born in clusters, in groups, like a lot of clusters, right? If you paid attention to the lectures, you have those giant molecular clouds. They have even like million solar masses. So they're going to form multiple stars. And those stars are going to be different. Some are going to be high mass, some are going to be low mass. So this picture over here shows you basically all kinds of masses of stars that are formed in the cluster. And you can see basically that on the main sequence, you have almost all of the stars. High mass stars are here, and these low mass stars, because they take longer to assemble themselves so that they can fuse, they will take longer to come on the main sequence. So what picture D shows you is that high mass stars are, they actually long time pass, so they have enough mass, they started fusing, they're all on the main sequence, and the biggest ones are leaving the main sequence. Those are these 2 points, okay? And the low mass stars in that cluster still didn't even get to the main sequence. So in my lectures, if you look in the slides, you can see that this, or in your textbook actually, the most massive stars, they only take, I don't know, 10, like few tens thousands of years to form. So let's say 50,000 years. So then you can see over here that this cluster probably is this highest mass stars already finished fusing hydrogen. So maybe this is like few million years old. That's what you see over here with this cluster. Now, when you move to the cluster B, what do you see about cluster B?
It's almost out of the main sequence and to the left, to the right, and many of them are gone.
Very good. So basically on this one, you see it's almost out of the main sequence. You put it really nicely. And so if I kind of try to see where the sun-like star would be, I can see that in these clusters, they're not, the sun-like stars are not there anymore. And so since I know that, let's say sun-type stars, they live up approximately 10 billion years. So then I know that this cluster is like at least 10 billion years old, right? So this is actually quite old, because only that those like lowest mass stars are left on the main sequence. And so then it's also like really cool to remind yourself about those 2 types of clusters, the open clusters and the globular clusters. So what kind of cluster would D be? Would D be open cluster or globular cluster?
1 second. Open cluster is the new ones, and globular is the old ones.
Very good. Excellent, Rose. I'm impressed. Okay. So yes, this would be like the open cluster, Pleiades, and this would be the globular cluster. Those like, you know, the clusters that I have in the lectures, that picture that only shows you like red, orange stars. So very old stars. And once again, it's really cool to learn that in our galaxy, we can find these globular clusters that are even like 13 billion years old, which tells you then that the universe has to be at least 13 billion years old. And that's pretty cool.
Oh.
Uh-huh. Okay, great job.
Do you want to do the star formation?
Me or Ryan?
Right?
Or the other two. There is Melissa, I think, and Sandra is there as well. So which one, Rose, that you would like?
A star formation, if someone wants to do it, or
The worksheet, you mean?
yes.
Yeah. Are you guys interested? Anyone?
Yep.
Yes? Okay, Ryan is interested.
Me too.
Who are you?
I'm Melissa.
Melissa. Okay, very good. So there were two worksheets: star formation and lifetimes, and stellar evolution. Which one you prefer?
A star formation?
Star formation. Okay. Okay, so this is from that lecture tutorial book. Okay, so who wants to go first? Let me actually just share it. Okay, so it's here. Who wants to go with the question number 1?
Okay. You are asking if the atoms will get closer or, you know, apart, and I say closer to one another.
Very good, because gravity tends. Very good. Okay, number 2.
What physical interaction of four chaos atoms do we have, as you described? Is gravitational contraction?
Gravity, yes, the force of gravity or gravitational interaction. Okay, perfect. What about number 3?
Would you expect the temperature of the center is increasing?
It's increasing. Very good. And then if you paid attention in the textbook, as the temperature increases and density increases, then the radiation will get trapped. So to think about it, think about the sun and how like photons that are produced in the core of the sun spend hundreds of thousands of years before they reach us, right, on the Earth. So the same with these stars. As it becomes denser and denser, the radiation becomes trapped, and then these stars start glowing basically in the infrared. So good. So that's number 3. How about now the table?
If someone wants to answer, go ahead. I have something, but you know, if someone wants to answer.
Yeah, somebody else.
Low mass.
Low mass.
The low mass, because you're given this table, right? And you can see what's the lowest mass star that you have over here.
0.5.
0.5, half a solar mass is. And you can see that that star actually is going to live 5 times more than the sun. And you can also, it's interesting to take a look at this star that has twice the mass of our sun. So that's like the Sirius, the brightest star in the sky is basically like this, 2 solar masses. So you can see, even though it's only like double the mass, it's going to live 5 times less. So that means, you know, you can have 5 stars like Sirius live and die in one lifetime of our sun. And then look at these really massive stars, like 60 solar masses. It's very, actually, these stars, you're not very likely to see them, statistically speaking. But if you could see them, they live like really short lifetimes, 360,000 years. Okay, very good. And then what else do we have over here? Oh, okay. Now, I already answered, I guess, this question. So what do you say? Melissa or Sandra?
I put greater than.
Much greater. Very good. Much greater. Okay, great. Number 6.
I have maybe something wrong, but star A will live 6 times longer than star B.
Okay. Star A, can I just see star A and... Okay, so one is, the star A is half a solar mass is, mass equal to the sun, okay. And the other one, okay. So this is not, okay, so they're like solar mass and 6 times the solar mass. Fine. So what did you say? Star A.
will live 6 times longer than B.
Okay. Everybody else, do you agree?
Because it's 6 times smaller than B, will be longer life.
I agree with you, but then take a look at the table, okay? So let's compare just the sun and 2 solar masses. So 1 solar mass and 2 solar masses. So if you are correct now with this question number 6, that means that the sun will live 2 times longer than this star that has 2 times the solar mass. Is that correct?
No.
No, okay. So then what do you say? What's the correct answer for number 6?
Well, it has 2, but it's not 2 times, it's 6 times.
I know, but you're saying 6 times because basically star B has 6 times more mass than the sun, right? And so you're saying it's going to live 6 times less, or star A will live 6 times more,
No, I
right?
think that because it's bigger, the bigger the star, the less life.
I agree. But is star A going to live 6 times longer? Is that correct answer? Somebody else, what do you say?
I put B.
As long,
Hmm?
8, 1, 6 as long.
No, Raúl is completely correct. The star A will live longer because it is like sun, and the other star is like 6 times more massive than the sun. And we know that the more massive the star is, the faster it will fuse. And the faster it will fuse simply because it has more gravity. It's going to create higher temperature in the core, and the fusion rate will go much faster. So even though it has more mass, more fuel, it's going to go faster through that fuel, and it's going to live much shorter lifetimes.
The correct answer is D.
Yes, the correct answer is C.
How do you do that math? Like I guess I don't really understand the 6 times longer and then more than 6 times longer.
Well, you don't have to do any math actually. So you can just look at this table, as I said. So they tell you one star is like sun, the other one is 6 times more massive. And so they give you these offers, okay? So immediately you eliminate first 3, right? So you know that it's either going to be D or E. The star A will live longer, right? And so now you have to choose, is it is it correct that, let's say, if I have star that it's 6 times more massive, it will live 6 times less. So I look now at my table. I don't have number 6, but I can take a look over here. Let's say I have sun, and I can see lives 10 billion years. And then I have something that has 2 times the mass, right?
Yeah.
And so then what would I say? If in this question that we are now talking, if you think that D is the correct answer, right? So 6 times more mass, 6 times less life, then if I have star now that has 2 times the mass of the sun, then its lifetime should be 2 times smaller than sun's. So sun has 10 billion years to live. So this star should have 5, if I'm correct with this thinking. But what do I see over here? Is not 5, but it is much less. So do you agree? So you don't do any math, but you just use this table kind of to figure out that relationship, that it's not going to be inversely proportional, 6 times more mass, 6 times less life. It is actually much less life.
Can I mention something?
Yes.
Can you go back to the table?
Yes, I can.
What was confusing to me, Ryan, is that they have 110 and 360 and looks like it's more. If you watch, one says billion and the other one says millions. And then you can see that it's less. The 110 is a million, and then 360,000. When you see the numbers look like more, but it's not billions, it's millions and thousands.
I know, yes, I know. They're intentionally confusing you. They want you to think.
The first time I see it was I don't understand why it's 2, one is 2 and one is 110 and the other 360, but then I read million and thousands.
Yeah, so you can think 110 million and then this is 2,000 million, right?
Down just by the size.
Yes. Okay, so and so this is important. This will come on the exam as well. So you should understand this. If the star has I don't know, n times more mass, it is not going to live n times less. It's going to live much, much less.
Yeah, I guess I don't really understand how it's six times the mass.
That's just the assumption.
Read.
Oh, it's the assumption. Well, then
No,
how would we know? How would we know that it's 6 times a star A will live more than 6 times longer? How do we know it's gonna be 6 times longer instead of just more than 6 times longer as opposed to just 6 times longer?
Well, I know that by looking at this table, right? So, so if, as I said, I don't know how differently to, oh, okay, I know. So here is the sun, okay? Here is the sun, 1 solar mass, and here is 6 solar masses, right? And so
Yeah.
you can actually read now their lifetimes. The 1 solar mass star will live 10 billion years, and 6 solar masses is going to live 110 million years.
Yeah.
Okay, 110 million years, that is basically 0.1 billion, right?
Yeah.
Okay, and so how do they compare? So is it 10 and then 0.1, let's say over here? How much difference is there? Is it 6 times less or it's more than 6 times less?
More than 6 times.
Okay, fine, great. Does that make sense now?
Oh, wait. I guess I'm confused on which is A and which is B.
So it's not from this table. That's what I got confused as well.
Oh, okay.
Yeah.
That's where I was getting confused. Okay.
So they say over here star A has a mass equal to the sun. So you can identify then in this table, okay, it's the second
I
one.
didn't even read the question. Okay, that
Okay.
makes sense. That's why I was really confused how I got 6 times. Got it.
Okay, fine. And the last question, who wants to do it? Sandra?
Sorry, I wasn't mute because I have background noise. The number 7, I said, is more than twice.
Okay.
Mm.
Well, let me read. A star twice the mass of the sun would have a rate of nuclear fusion that is more than twice the rate of the fusion of the...
Mm-hmm.
Yes, very good, because it's going to live much less. Okay, so it goes much faster through its fuel.
Why?
Mhm.
I had to explain why.
Okay, Sandra, you want to explain why more than twice?
Hold on, I'm still reading. I did it this yesterday, and right now I'm confused. I don't know.
Okay, fine, but you could actually take a look over here because in the table you have the star that has twice the mass of our sun.
Mm-hmm.
And you can see that it's going to live only 2 billion years. Okay, there is some noise coming from somewhere. Okay, so we can see then that that star that has 2 times the solar mass will live 2 billion years. So just look over here. So the sun will live 5 times longer, even though it has half the fuel. So what does that tell you? How many times this star is fusing faster? The star will live 5 times less, even though it has double the fuel, double the mass. So basically, it fuses 10 times faster. Does that make sense?
Oh.
Yes?
No.
Why not?
I don't understand where the 5 is coming from.
So I can see that sun lives 10 billion years and the 2 solar mass star lives 2 billion years. How many times more does the sun live?
5 times.
5 times. Do you agree?
Yes.
5 times lives more. And how much fuel does the sun have? Compare half, right? Half of what this one has, right?
Mm-hmm.
This one has 2 times the solar mass. Sun has only 1 solar mass. So sun lives 5 times more, even though it has half of the fuel. So for that to be possible, that means that sun fuses 10 times slower. Or if you reverse it, then that means that this star over here, 2 solar masses, fuses 10 times faster than the sun, right? Does that make sense?
Yes.
Okay.
Thank you.
You're very welcome. Okay, and do you wanna, how about the other one? Was the other one easy?
Yes, because it's more or less like the one of the exercises that we did.
More or less like the homework, right?
Yeah. It says that it's an open answer because everybody will have different.
Let me see, I forgot, so I'll open it. Yeah, so this one is very, you're right. Okay, let me just share it.
Only the beginning is the same. Well, pretty much the same.
Okay.
To the small mass goes to planetary nebula.
Okay, so this one is good because once again, you get this summary, what is happening depending on the mass. Less than 8 solar masses, more than 8 solar masses. And then you can take, oh, okay, so it gives you the answer over here with a binary star and all of that. And then you have to fill this in, these bubbles.
Yeah, to the left side, the small mass will be a planetary nebula.
Yes,
And then the white dwarf.
yes.
And then we, under the white dwarf, we put the binary companion star. Under white dwarf, yes. And will become nova and type 1 supernova.
Okay, very good, Rosa. So basically you put white dwarf here and then you say if it has companion, it can go nova or supernova type 1. Once again, don't worry if you don't know what those are because we will learn about them next week. And then over here with large masses, what do you need with large masses?
Type 2 supernova.
Excellent, always. And then what do you leave behind?
A neutron star or a black hole.
Super, that's it.
No, there is more. Black hole has a binary companion star.
Okay.
Well, I put this. Accretion is going to create more temperature and emit large amount of X-rays radiation.
Mostly gamma rays, those those are going to be those gamma ray bursts if there are two black holes. Well, depends what's the companion to the black hole. Okay, but fine.
More than X-rays gamma?
Yes, gamma rays.
Thank you.
You're welcome. Again, don't worry about that. It will all come in the next chapter. So here is the goal. Like if everybody can understand the difference between low and high mass stars, and what elements do low mass stars fuse and how they die with the planetary nebula and leave behind white dwarfs, and then high mass stars, they fuse all the way up to the iron. They explode supernova type 2. Hopefully you understand that supernova type 2. And then what is left behind without any details of those objects, because we will talk about them next week.
Professor?
Yes.
I just got a heart attack when I opened the computer today because you already put the next week in the computer.
Oh, did I?
I put week 12.
Well, it wasn't my intention, only maybe if I made a mistake.
We don't have to go through that now, isn't it?
Wait, let me see. So you're saying in your class that I put the next week? Oh, okay. I'll hide it from you. Sorry, I was working on that.
It's good to have it, but I just hope that we don't have to do it this week. Because
Okay, good. Sorry, I'll hide that from you. I was editing some things there, so that's.
It's good, but it's just that I just want to get sure that we don't have to do anything for this test.
No, not at all. Not at all. So just these things. And you did great. I'm pretty impressed. Okay, good. Any other questions?
No, thank you.
Nobody?
All good.
I'm good.
Okay, so don't forget next week we have extra credit talk if you can make it Thursday night for the search for the life outside of the, I guess, Earth. So looking for ETs.
I like that one. Thank you.
I'll be there as well. See you guys.
Yeah, thank you.
Bye
Bye,
bye.
thank you.
Thank you. Bye.
Bye bye. Good night.